Coriolis effect is often cited as the reason that toilets flush one direction in the northern hemisphere and another direction in the southern hemisphere. And while this isn't really the case, this has more to do with the shape of the toilet bowl or the way the water enters the bowl. The Coriolis effect is still very real. And the Coriolis effect, what it does is it deflects objects moving in a rotating frame of reference. So one rotating frame of reference is the Earth. And so we're going to talk about how the Coriolis effect deflects moving volumes of air as they move along the Earth's surface. But before we do that, let's explore the Coriolis effect in a slightly different setting. Let's imagine that you and your friend go to the playground, and at the playground there's a certain type of playground equipment, a merry-go-round. And you might have seen merry-go-rounds before, you might have played on merry-go-rounds before. Essentially they're discs that can spin freely, and people like to run alongside them and get them going really fast, and then other people will lay down or sit down on them and experience what it's like to be in a rotating frame of reference. They're really kind of dangerous, but also a lot of fun. So let's say you and your friend go to this playground, and I'll represent you and your friend with these smaller circles, and you want to play a game of catch. So you go to the center of the merry-go-round, and your friend goes to the edge of the merry-go-round. And if the merry-go-round's not rotating, then when you go to play catch, it'll be very simple. You'll just throw the ball from you to your friend back and forth, and it's very easy. But what happens when the merry-go-round is rotating? How will that affect your game of catch? So let's imagine that the merry-go-round is rotating counterclockwise viewed from above. So in this direction like that. Well, what's going to happen? So as you throw the ball to your friend is going to be moving, and as the ball's in midair, your friend will rotate, they will move away from where you threw the ball. So how will it appear as though the ball moved in your frame of reference? What will you and your friend observe to be the motion or path of the ball? Well, you'll throw the ball towards your friend, but then it's not going to get to your friend. It's going to be deflected. Your friend moved while the ball was in midair, so it'll look like the ball was deflected, and it will look like the ball was deflected to the right. It'll look like the ball turned to the right. Well, how about if your friend throws the ball to you from the outside to the middle? Well, as your friend is on the edge and we have the rotating merry-go-round, your friend will have some component of their motion tangent to the merry-go-round. They'll be moving tangent to the merry-go-round. So I'm going to put an arrow here to help us think about that. So they'll be moving like that. And then as they throw the ball to you, you'll have to add this motion into the motion of their throw, and so it'll be deflected. It'll be deflected in this direction here, like the arrow shows. And so it'll look like the ball followed a curved path, and then it was deflected or turned to the right. So whether you throw it from the inside to the outside, or your friend throws it from the outside to you on the inside, the ball was deflected to the right. Well, let's think about now what happens if the merry-go-round is rotating in the other direction. So we'll make a copy of this, and we'll move it over here. And now the merry-go-round, viewed from above, is turning or rotating the other direction. It's rotating clockwise from above, so direction like that. Well, now let's think about what happens. So you throw the ball to your friend, but the merry-go-round will rotate while the ball is in midair, and so it'll look like the path of the ball was deflected. And in this case, it'll look like the path of the ball was deflected to the left. Similarly, if your friend tries to throw the ball to you from the outside to the inside, because they have motion tangent to the circle, tangent to the merry-go-round, the ball will be deflected. So I'll draw an arrow for that tangent motion. And when they throw the ball, it'll be pushed in this direction, and it'll be deflected to the left, just like when you threw it to them. So if the merry-go-round viewed from the top is rotating clockwise, then the ball will be deflected to the left. Alright, well, how does this transfer to the Earth system, to the rotating Earth? Well, so if we imagine that we're viewing the Earth from above the North Pole, then the Earth rotates in this way, counterclockwise. So this example here on the left is analogous to you being at the North Pole, and your friend then here towards the edge that's analogous to being at the equator. So this situation is like the northern hemisphere, or how things move or deflected in the northern hemisphere. And then in this case, viewed from above the South Pole, the Earth rotates clockwise. So in this case, this is like being at the South Pole. And then your friend here at the edge, again, that's like your friend being at the equator. So now let's view the Earth edge on and see how this all fits together, how this relates. So here we have the Earth. And now instead of imagining playing catch, throwing a ball, we're going to imagine a volume of air moving along the Earth's surface. So I'll go ahead and draw a square to represent that volume of air. And let's imagine it moving from the North Pole south towards the equator. Well, that's just like this example here, where you're in the middle and you throw the ball and it was deflected to the right. So in this case, this mass of air is going to turn to the right, or be deflected to the right. And what about moving from the equator north to the pole? Well, that's like your friend throwing the ball to you, and again it was deflected to the right. So that will look like this, deflected to the right. How about the southern hemisphere? Well, if we have a volume or parcel of air that's moving from the South Pole north to the equator, that's like this example on the right, where you threw the ball to your friend, and we saw that the deflection was to the left. So this mass of air will be deflected to the left, like that. What about moving from the equator south towards the pole? That's like your friend throwing the ball to you, and again the deflection was to the left. So the deflection was to the left. So like that. So now we see that volumes or parcels of air, as they move along the Earth's surface, because the Earth is rotating like this, because the Earth rotates from the west to east, parcels of air are deflected. They don't move in straight lines over very long distances. And it's this deflection of these volumes or parcels of air that help to set up large-scale atmospheric circulation patterns. Circulation patterns like the Hadley cells and like the jet streams, which will be discussed in another video.